Hi everyone. In this tutorial, I wanted to show you how you can create what is called a depth map or a depth distance. If you know space syntax, a whole field of spatial analysis, you will know what a depth distance is. Basically, it is the topological distance from one point in a graph or one vertex in a graph to all the other points. Sometimes you can accumulate them and create a depth map for the whole graph. Or you can calculate the depth map for all the points with respect to one original point, and this is what I am doing in this tutorial. The other way would take a bit too long, but I just wanted to show you some of the images that you can get out of this type of analysis, like you can analyze street networks or interior spaces. So how do I do this? So let's get started on explaining this graph. It's a little bit involved. It has a couple of tricks in it, but nothing too difficult. So as usual, we're going to start by creating some sort of input geometry. In this case, I decided to use the torus that is input in Sverchok and change the sections and spin sections as well to increase the density of it. And then I did a topology by geometry right here. So now we get a cell out of it. And again, as we mentioned in the previous tutorial, in order to get the dual graph of a cell, and you want it to be regarding the faces, you need to convert it into a shell, because the dual graph of a cell is a single vertex, so we will not get any information out of that. But the dual graph of a shell is a wire that connects all the centroids of all the faces. So we create a graph by topology here using the simplest option, which is the direct option. And then what we are going to do here is find the topological distance between one vertex, one chosen vertex, and all the other vertices. So what we're going to do is create a vertex by coordinates at 100.3, which is indicated by this small cylinder that you can see here on the left. And from the list of vertices, of all the vertices, in the graph, which is now 1536 vertices, we feed that in and we find the nearest one, all right, to this one. And we are drawing that. So you see it here. This is basically, we are drawing a cylinder at that location. So if I just hide that, you'll see this cylinder is going. Let's change the position of the cylinder to see the effect on the depth map or the depth distance that we see here. So I'm going to take this x value. It's now at 1, so I'm going to put it at -1 over there at the opposite end. So I'll type -1. And in a few seconds, it will update. It will now update over there, and you'll notice that the faces that are closest to it are in dark blue, and then they gradually go through greens and oranges, yellows, all the way to red. So basically this point here at the bottom is the furthest distance from that point. It's important to note also that I'm using a topological distance, meaning it's an integer number, basically how many steps you need to traverse in order to get from one point to the other, rather than a linear distance. So it's actually taking into account that you have to go around the circle and maybe down at a certain point in order to reach it, based on the shortest path. But it is an integer number. It's called a topological distance rather than let's say, a metric distance. And this is the node that you see here, graph.topological distance. So for this node, we feeded the graph, we feeded the vertex that we are interested in, and then all the vertices, and then we get a list of distances from that node. So how do we get the color? So I have created my own color by number in a range. I know Sverchok has really advanced ones, but I need to be compatible with Topologic and in other platforms, and they use a simpler color by number in range. So what does this node do? It basically takes a number or a value and then a range, a minimum value and a maximum value. And based on the location of that value within this range, which is basically, let's say, a ratio. So if you have a range from 0 to 1, the value could be 0.5. And based on that ratio, it converts it into a color on the color wheel from dark blue to bright red, going through the oranges and the blues and the greens and yellows and all of that correctly, and it gives you a color value. You have the option to use alpha, which is the transparency. If you want that, that is a set value here at 0.5, and I said yes, go ahead and use it. And I'll show you a bit later what we do with that color. So now that we have the distances, and what I did to find out the maximum of the range is I found the maximum distance. So I know that the maximum topological distance is 44. Based on that, I did a range from 0 to 44, and that's how I get my colors out. So you can see the colors here as tuples, 4 values, with alpha being the last value as 0.5. So how do we get the display to look so nice like this, with all the colors on this? If you remember from my previous tutorial, I said that a graph.vertices does not guarantee the order of vertices. It always changes. Every time you run it, it might give you a different order for the vertices. So what I had to do is get the faces of the torus. So that's what I'm doing here. And then get the centroid of these faces. And then again find the nearest vertex to these centroids from the list of graph vertices. So I basically match this list to that list. Now it's going to take a while, obviously, because I'm searching for 1536 in another list of 1536. So this is going to take a little bit of time. If you use the KD tree method, it might actually do it a bit faster, but I would love for somebody else to experiment with that and report on it. So once we have now the list of vertices correct, so basically we have sorted this list of graph vertices by the list of centroids, we are now able to calculate the topological distance based on a nicely sorted list of vertices. So this list will match now the list of faces. So now if I draw these faces one by one, so I convert them to geometry, and then I draw them here, I can then choose the color as it comes out from that whole process, and I feed that into the color here of the faces. So you'll see that once I have changed this to a color, I feed that into the color input here, and that is how I get my nice kind of rainbow colors on it. And this is really it. Let me just exercise it for you a little bit. For example, let's go ahead and change the y to -1, just to put it on the 4 corners. Oops, what did I say? X should be 0 probably, so that it goes to that corner. Here we go. And the reason you're seeing a bit of shimmering is because I have the alpha at 0.5. If you wanted it to be absolutely solid, just change it to 1. And you can see a little bit that this, the colors better when you are zoomed out of it a little bit, and you can see what happens there. Or I can change the y to 1. And there it is. Thank you for watching.